A cart on a linear air track has a uniform acceleration of 0.172 meters per second squared. What is the velocity of the cart after 4 seconds if it is released from rest? The equation for this is that V final is equal to AT plus V sub naught, which in this case is going to be 0.172. We will have our time of 4 seconds, and we will have our initial velocity of 0. So that comes out to be 0.688 meters per second. Number 2. How far does the cart in question 1 travel in 1 second, in 4 seconds if it is released from rest? There's a couple of equations we could use here. We could use the average velocity times the time. The average velocity is going to be the 0.688 that we calculated in our last one divided by 2 times 4 seconds. Or we can use 1/2 AT squared, which will be 1/2 times our 0.172 times t squared. Either one of those will give you 1.376 meters. Number 3. An air track, like the one shown in figure 4.2, here is figure 4.2, has a block with a height of 12 centimeters or 0.12 meters under one support, and the other support is d equals 3.5 meters away, and that's this distance here. Along the track. And what is the angle of inclination? Here we have an angle here, opposite and hypotenuse. Sine theta equals 0.12, the opposite, divided by 3.5, the hypotenuse. So theta will be inverse sine of 0.12 over 3.5, or 1.96 degrees. The following set of what is the acceleration of a cart parallel to the air track? Okay, so here we have gravity acting downward, and the gravity is split into 2 parts, the normal part and the parallel part. The parallel part is mg times the sine of that angle there, which you can determine is the same as this angle by noting that this is a perpendicular angle. This is theta prime plus theta plus 90 degrees is 180 for both the inside of this rectangle, or the inside of that triangle, and the straight line going across there. So anyway, mg sine theta. Okay, notice here that if I rounded twice I got an angle of 1.96 degrees, but then I used that 1.96 degrees and got 0.335. However, since sine of this number is 0.12 over 3.5, I can also get it straight away by just taking that factor times 9.8 and get 0.336. I'm going to use 0.336 because that didn't use any rounding. Alright, next question. The following set of data were taken for the displacement x of a cart on an air track as a function of time t. Calculate t squared for each of the data points, and then perform a linear least squares fit x versus t squared, where x is the ordinate and t squared is the abscissa. basically we're looking for an equation in this form. A slope times t squared plus a constant. This is the abscissa, t squared, and x is the ordinate. So I've copied all of the data into a spreadsheet, and I'm going to get the values of t squared equals this value squared, and copy that over. And then what I'm going to do, let's start with the linest equals linest. And the y's, remember, this means the ordinate. So the ordinates were these, comma, and then the x's, which is the abscissa, this one, and then the we're going to say true because we want b to be calculated, the y-intercept to be calculated normally, and true because we want additional regression statistics. Namely, we want r squared. So this is our slope, this is our y-intercept, and this is our r squared. So what can we say about this? First of all, before I go on, I'm going to try to come up here and, okay, I've got a little trick to use because I'm going to try to make a graph. And in order to make a graph, a scatter plot, I really need things to be abscissa then the ordinate, because I don't know how to do it otherwise. So I'm going to select this range of data. So it's got the abscissa first and then the ordinate. And I'm going to insert a scatter plot, and there's my scatter plot. I'm going to do a couple of things here to modify it. First, add a trend line, and then let's see, okay, right click, format trend line, and I want to display the equation on the chart and display r squared on the chart. Okay, notice it says y equals that and then r squared. So I want to change that. So I'm going to right click on that and then just say edit text, because I don't want that y there. I want an x. And I don't want that x there. I want a t squared. And so now the trend line represents what I want it to represent. So I'm going to see how this matches up over here. If I can move it, there it is. Okay, so we've got the slope of 0.157309, the y-intercept of negative 0.0195, and the r squared of 0.998451. So if I want r, that is going to be equal to the square root of this value here. So 0.999225. So I'm going to use the values over here in the linest and copy them over 0.157309 and 0.999225. Let me talk a second about a least squares fit. Imagine that I've got a few data points, like maybe this and I decide I'm going to draw a trend line through that data that looks like that. Okay, what then I'm going to draw a vertical line from the trend line to each data point. And then I'm going to turn those into squares. So this is a square, and this is a square, and this is a square. This is a square, and that's just a little bitty square. Okay, so the idea of the trend line of a least squares fit is that by pointing that line in a particular direction through the data, you minimize the area of those squares. And the way you would express the total area of those squares is with the sum of your y value minus, and we'll call y hat equals mx plus b is the trend line. So y is the actual value of the statistic, and y hat is the okay, let me say that again. For this one, this point is y, this is y hat. And for this one, this is y, this is y hat. So the number on the trend line is y hat, and the number off the trend line is actual y. Here, the measured y, the predicted y. Here, the measured y and predicted y are about the same. So the total area of all of those squares is y minus y hat squared. That is going to be called the unexplained variation. Okay, now I'm going to make some of these marks in pen so they can't be erased. And I'm going to make that mark in pen, that mark in pen, the actual measured points, and that mark in pen. Okay, those are like where the actual measured points are. And then I'm erasing all of my trends. And we're going to draw something else. And what's this line? This is y bar. This is the actual mean of those 5 numbers. 1, 2, 3, 4, 5 numbers. All right. Now we're going to do the same thing with y bar. We're going to have this square. That's a big square. This square, little square. This square, and this square. I'll draw it this way. And this square, about the same size as the other one. And the total area of all of those squares is sum of y minus y bar squared. And that would be the total variation. Okay, that was fun. Now I'm going to erase all those. I'm going to erase all those and put the trend line back in, and then discuss y hat at each of these points, y hat, compared to y bar, which is right there, y bar, and draw a square, for each of those. Y hat and y bar, 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 y hat and y bar. And the sum, all of those squares, y hat minus y bar squared, is called the explained variation. Now, I'm not going to try to prove it, but the total variation is equal to the explained variation plus the unexplained variation. They actually end up coming out to a nice, neat sum. And r squared is equal to the explained variation, sum of y hat minus y bar squared, divided by the total variation, sum of y minus y bar squared. So it's equal to the explained divided by the total. So in that case, this says basically the 99.85% of the variation in x is explained by the variation in t squared. So our general kinematics equation says x is 1/2 at squared. There would be a plus v sub naught t plus x naught. We didn't have any initial velocity. We might have had some discrepancy in the measurement devices that would account for a 1.9 centimeter offset of the distance. But in general, we can set this so it's 1/2 times 1/2 a is equal to 0.157309. So multiplying both sides by 2, we get acceleration of 0.314618 meters per second squared. Question 6. We've already talked about r squared, and that r squared equals 0.9985 or 99.85%. So 99.85% of the variation in x is explained by a linear correlation with t squared. There is a table in the back of, well, I have provided it to you, correlation critical values.pdf, and it shows that n of 7, because we have 7 data points, alpha of significance of 0.05 is 0.754, and the significance of 0.01 is 0.875. So here I've copied that table, or the relevant line from that table, that for n equals 7, the alpha equals 0.05 significance, r is 0.754, and r is 0.875 for the 0.01 significance. Since our r value was 0.999225, we can say